Welcome back, everyone. I'm John Furrier, host of theCUBE, here at theCUBE's NYSE studio. Of course, we have our Palo Alto studio connecting Silicon Valley here to Wall Street. This is our Robotics Physical AI series, and Qiqi Wang is here. He's the co-founder of Flexcompute and also associate professor at MIT, course 16, if everyone's interested. So that's really critical for a lot of the AI infrastructure. Also space and defense tech. Qiqi, thank you for coming into theCUBE today at the NYSE.
Yeah, thank you for having me. It's my pleasure.
The Space Tech Conference is going on upstairs. Thanks for breaking away for some time. You know, the physics, AI, all kind of rhyme together. And you look at all the infrastructure build out we've been covering on our AI Factory series is also translating right into robotics, physical AI. Defense tech is a big part of that. And you see drones, you see physical AI, robotics in the field. No better case study than to solve the hardest problems in space. You have a zillion PhDs on your staff. I looked at the site, not a zillion, but many.
Yep.
You guys are pioneering in that. Explain what you guys do, then I'll get into some of the questions.
Okay, Flexcompute, as we said, is a physics intelligence company. And we provide the technology for engineers and now increasingly AI agents to ask physics questions. And this is the kind of questions like what if questions that really underpins all human ingenuity. So physically what that means is that we expose the APIs and now increasingly model context protocols so that engineers and the agents can really ask the quantitative physical questions and get answers at the speed of thought instead of having to set up like clunky simulations to get results. And you can think of it as providing a collaborative physical brain, right? So that people can work with to design their product and figure out hardware solutions that nobody...
So it's really assisting the human.
Yes.
That's the print, not replacing or using. I mean, people lean on AI a lot, but the power users of AI are the ones that drive it.
Yes, it's really enabling the human engineers. And basically, we build the product as we wanted to use it ourselves.
By engineers, for engineers.
Exactly.
All right, let's talk about the origination story. Did it come to you? How did this idea come to you? I mean, obviously, we're seeing AI move out of language to vision. I mean, I see biology models. You got physics, natural progression. Where did this idea come from? Well, tell me the origination story.
Well, the originating story is a little bit more mundane because we looked at how engineering software has been stagnating for decades. You know, like consumer software has been evolving revolutionarily almost every few years, right, over the past few decades. But engineers has been using pretty much the same tools since like 1990s.
Fortran. I won't even bring that name up. Remember, the equipment was all run on Fortran code. No, but it's antiquated.
Yeah, it's antiquated. And we as engineers ourselves, as you said, I'm a professor in aeroastro, right, feel the pain firsthand. So the founding team of Flexcompute are really engineers like me, right? We have a lot of expertise in high-performance computing, but we are also spending a lot of wide range of physics and engineering disciplines. And we came together to really build the tools that we and our colleagues wanted to use. So since the beginning, basically the idea or the motto is to use advanced computing to accelerate innovation, and specifically to make innovation in hardware to be as fast and as easy as innovation in software.
You know, and robotics is a great example of some of the innovation speed. I mean, the velocity of the innovation in robotics has been off the charts. We've been seeing great progress, mainly because, one, the compute's available. You got hardware, which is grounded in software.
Yep.
We see that with NVIDIA. Everyone talks about CUDA and the relationship they have. But that's applying everywhere. Talk about that dynamic of the software relationship to hardware and how that's impacting the engineers, because engineers look at hardware and software as one thing. Most do, but you have specialists that do hardware, specialists do software. But talk about that blend between software and hardware and how it relates to Flexcompute.
Well, So software engineering has been very easy in some sense, right? Because every time you change the code, you hit compile, and the code actually runs. And if there is any bug, you see it immediately, right? And if it behaves in a way you don't expect, you also see it immediately. Hardware is different in the sense that when you change your design, you either have to physically build it and test it, or you have to test it in a computational simulation. Either way, it takes tremendous amount of time. And there is a lot of things involved, not just the physics, but the geometry. When you change your design, it usually involves changing geometry. And there is a lot of friction in the process. And that is one of the things we are changing, as I can give you some examples later on.
Yeah, so let's talk simulation. I want to get to the example. Let's talk about, you mentioned simulation. Simulation has been a great advantage for using synthetic data, looking at digital twins. But when you look at physics, you have scenarios of actual properties. How has simulation changed, and what do you guys do differently?
Yes, so simulations has been a great enabler, right? Basically enables people to not really have to build the physical things and test it. And the space is a great example. Building things and testing space is extremely slow, and you have to wait for it to launch and things like that. So simulation for space is especially important. But simulation tools has been really stagnant for a while, and that's because all the simulations has been built on CPU platforms. And in order to even run one simulation of one design, one operating condition, engineers has to wait for hours, sometimes even days, for that simulation to finish. So that becomes really the pacing item for hardware innovation, right? The bottleneck for hardware innovation has not been the vision of what could be built. It was not the ambition for building things that people envision could be built. It's not engineers' ingenuity, it's the tool. It's the tool that has been throttling how much we advance in hardware engineering.
Yeah, it's limiting at big time. You know, one of the things about space, since you mentioned it, this is focus, in your focus, is that it's hard to unwind that. You launch something into space, it's up there.
Yes.
If it runs out of battery and fuel, it's over. And if it breaks, you can't send the technician up. You can't upload. You can kind of upload, I guess, now software, but the hardware has to be tested.
Yes.
Talk about that requirement. That's pretty stringent. That's a constraint. How do you guys look at that? And give us some examples of how you guys are working with things like that.
Yeah, that's a great question, right? So I'm going to give an example of us working with Northrop Grumman. And the example is with spacecraft docking. And for people who are not familiar, spacecraft docking, as you said, it's an extremely high consequence and also incredibly dangerous maneuver. And this is because you have to fire thrusters, rocket thrusters, to position yourself to dock and also to decelerate. And these thrusters can easily push your target into spinning. And if your target is spinning, you cannot dock, right? It can also literally melt and damage through the hot gas from the thrusters, different components. And also you may risk depositing unburned propellants into sensitive equipment that can also terminate the mission. So this is an extremely critical application in which engineers absolutely have to prioritize the accuracy of the simulations of how the plumes of your thruster behave in the vacuum of space, right? And the Northrop Grumman engineers 100% prioritize the accuracy over anything else. And that's why each simulation takes weeks. And in order to plan one single docking maneuver, it takes months of simulations to do that planning. And we completely changed that. Our AI model, our physics AI model, enables such planning to now be performed in real time rather than over months.
So two things happening. One is the compute was slow. I mean, I talked to someone at Boeing once on theCUBE, did an interview, and doing wing design, just all the variations of what could happen on an airplane.
Yes.
It's too complex. It would be weeks before they get their models back. Now, so GPUs come. Thank you very much. Check. Now the AI software. Talk more about that AI software advantage, and because now you get the perfect storm on the tooling, because you got the GPUs
Yeah.
and you got the AI. Talk about that
Yes.
piece.
Yes, so the coupling between the GPU computing and AI is critical. Actually, there is also a third piece, that's the geometry handling, right? So Flexcompute built our infrastructure around the three pillars. One is the GPU computing. The GPU computing, we have a simulation of foundational physics, including fluid dynamics, right? Fluid dynamics covers the rarefied gas that's happening in space. We also have structure, we also have electromagnetics, we also have thermal. That's one of the most important part. And the second part is actually geometry. So we use AI to automatically handle geometry that resolves one of the most important bottleneck of simulation. That's the manual processing of a lot of the geometry. And these two components really enables the AI part that makes it possible to train AI that engineers can trust in this kind of critical applications like spacecraft docking.
You guys have a lot of customers. You mentioned one, the docking one, that's very complex. Talk about some of the other customers that you're engaging with. Share some of the use cases in the physics world and space. What else are you working on? You got a wide range. I mean, physics is everywhere. I mean,
Yes.
the laws of physics, I've heard that quote many times. Speed of light, laws of physics. You know, you can't really change physics, but you
Yes.
can understand them.
Yes. Yeah, so our customers really covers a big range. So in aerospace and the defense, we have Northrop Grumman, we have Embraer, we have Joby Aviation, who is being listed
Yeah.
as of today, and yeah, we have a lot of other people who are doing defense, and we have Jet Zero. So, but apart from that, we also have a lot of customers in semiconductors. We have Samsung, we have Global Foundry, we have Xanadu, we have basically a lot of the people who are not just designing the most innovative aircraft and spacecraft, but also pushing the limits of both silicon and quantum computing.
So basically anything with material science involved, you can play.
Yes.
Because chips, they're not in space, but they will be in space.
Yeah.
Space is natural because you have the tooling. So it comes down to the tools. You're building the tooling layer to be very compatible with engineers.
Yes. I mean, physics is physics, right? Basically, we provide the physics layer, and wherever that particular physical disciplines found the application in engineering, we have a customer.
All right, what's next? Tell us what's next. And how old is the company?
Well, what's next is I talked about the three pillars, right? And the first pillar is foundational simulation, and we are just going to be deepening that layer by involving more and more physical disciplines. And we are also going to be improving our geometry AI capabilities. And that is going to allow us to expand into more engineering applications that has high consequences, right? And our principle is to train physical AI that doesn't really just approximate the behavior of these physical laws, but really train them to understand the physical laws themselves. And that's kind of the difference between AI models that works just most of the time versus AI models that engineers can trust.
You're optimizing for accuracy because of the criticality nature of what you do for a 100% accuracy.
Yes, we are optimizing for trustworthiness, right? For example, in the spacecraft docking application, we are not training AI models to approximate the behavior of the plume of the rocket, of how it reflects off a spacecraft, how it forms a shock layer. No. We are training the AI to understand how one molecule interacts with other molecules in such interactions, right? So this is a philosophical difference of what the AI actually does, right?
Yeah.
And that makes the difference between AI that works
You're rooted in engineering principles,
exactly.
and you unpack the key elements and train it on that with the
Yes,
geometry piece.
exactly.
Okay, so how old is the company?
The company is a little bit more than a decade old.
Okay, so you got a lot of PhDs, you got a lot of staff, and train it on that with the
Yes,
geometry piece.
exactly.
Okay, so how old is the company?
The company is a little bit more than a decade old.
Okay, so you got a lot of PhDs, you got a lot of staff. How's it going at MIT? Good recruiting there. A lot of brainiacs go to MIT.
Yes,
You
very
know,
good.
because you got a lot of PhDs.
Yes.
Talk about the MIT angle here. Actually, you teach a class there. A lot of smart people at MIT. A lot of PhDs. What's it like there? A lot of PhD students. You're recruiting there. What are some of the things that? What's the culture like?
Yeah, so this is very interesting because at MIT I see a lot of great students, and I can also collaborate with all kinds of professors, right? The whole MIT is, I can say, a huge physics department in the sense that people, even in different engineering departments, works on different physics, right? And we can work with a lot of different professors. We can recruit from different groups into Flexcompute. And inside of Flexcompute, the culture is very much academic, right? People collaborate with each other, but with a key difference of working on together on problems with significant engineering consequences. So that's what I found the most fascinating about the culture of Flexcompute.
Yeah, PhDs like to solve hard problems, and you got one of them. Final question for you: upstairs at the space conference here at the NYSE, what's some of the conversations like at the inside the building today? What are some of your peers, and what's the industry's top issues being worked on?
Oh, there is a lot of great issues, and one of the most fascinating thing I found the conversation upstairs is I came over, right? This is NYSE, and I was expecting to talking to executives and the business people, but what I found is a great mixture of a lot of leaders who are very, very deeply technical, and we understand each other immediately, and this is a great sign for the future, right?
Yeah.
And what I expect from today's conversation is that the next few decades is going to be as innovative as software for the past few decades. Yeah. So back in the 1980s and the 90s, nobody, I say nobody, can predict the kind of a software ecosystem we're using right now. Nobody can predict the internet we are surfing right now. Nobody can predict the array of gadgets we carry with us today, right? I would say the next few decades for space is just going to be like that. And I expect that today, none of us can predict what we have in 20, 30, 40 years from now. And the Flexcompute is building the physical intelligence layer that's making that possible.
Well, you're a frontier leader, and it's going to be all unexpected. The future's unwritten, and you guys are doing a great job. Thanks for coming on theCUBE, and we're doing our part here. NYSE's got a great community, a lot of technical people, not just finance and business. Got a great community. Of course, the NYSE Wired, theCUBE's brand program is doing our part. Thanks for coming on theCUBE. Appreciate your time.
Yeah, thank you for having me. It's a great pleasure speaking with you.
Okay, I'm John Furrier, host of theCUBE here at theCUBE's NYSE Wired program, an open community. Of course, NYSE bringing the leaders together, the frontier leaders. Thanks for watching.